have got various type of processes such as stable process, unstable process and integrating process. Apart from the stable, unstable and integrating processes, we have also lag dominated and delay dominated processes. Smith predictor controller is generally used for delay dominated processes, and we are going to discuss about the conventional Smith predictor controller and some advanced Smith predictor controllers in this lecture. Let us see the limitations of a process, the limitation of a controller in controlling a process with large date time. Now, we have a process here which has got a large date time. So, the process model be given by G s is equal to 5.6 e to the power minus 95 s divided by 40 s plus 1. So, we have a stable process with large date time or delay. When it is subjected to a PI controller of the form G P I is equal to 47, some value is not appearing here. Anyhow, when we have got a controller such as your magnitude is 0.05, I think here that is not shown. So, controller of the form 0.05 1 plus 1 upon 47 s, which can ultimately given in the form of 0.05 times 47 s plus 1 upon 47 s. Then, what type of time response we will have from this closed loop control system, that we will see. Now, the process input, the closed loop system input is unit step input signal, whereas the process is subjected to a static load disturbance of magnitude minus 0.1. So, when the PI controller is employed to control this process with large delay or dead time, then the type of time response we obtain is shown over here. Here, where you see the settling time is approximately of a value greater than 800 seconds. Although the time response has got less overshoot, the settling time is very large, and this is your delay of 95 seconds. Again, the load disturbance is also not acceptable, because the load disturbance magnitude was minus 0.1, whereas the undershoot you have got or the overshoot you have got is quite significant. So, this is one of the limitation we have with the performance of a controller in controlling systems with large date time. To overcome this problem, Smith proposed a Smith predictor and controller structure. This is the conventional Smith predictor control structure. Conventional Smith predictor controller. How it is different from the single loop control system we have for controlling processes with small dead time? I can represent this in some equivalent form to make out the difference. Let me redraw the conventional Smith predictor controller structure. You have GC with inner feedback of G M, and you have now G to the power minus theta s here is the output y, input r, and we have G m e to the power minus theta m s over here. So, this is the equivalent structure of the Smith predictor controller. So, the controller is effectively now G C upon 1 plus G C G M. Then, what is fed back to the controller? The error signal is made up of the signal we get from the output we get from the actual system dynamics and the system dynamic model. In the event of matching of the two outputs, the output from the original system and that from the model, then the signal through this path will be 0. I mean, when G m e to the power minus theta m s is equal to G e to the power minus theta s, then what will happen? There will be no signal, therefore, I can break this path. Then the output of the system will be simply equal to G e to the power minus theta times G c 1 plus G c G m into R. So, as if you have got a open loop control system where the controller is this one and the system original system is this one. So, effectively the time delay term is taken out from the denominator of this expression. There is the difference, major difference we have from that of a conventional control loop, because as far as the output and reference input are concerned, if I denote this by the controller by G c and that by the system dynamics by G e to the power minus theta s, then y s will be equal to G c times G e to the power minus theta s upon 1 plus G c times G e to the power minus theta s into R s. You see the delay, time delay term is present in the denominator of this expression, whereas when you employ a Smith predictor controller, then the time delay term can be removed, eliminated from that from the denominator of the transfer function or the expression for the output, provided the dynamics of the model, transfer function model exactly matches with that of the system or plant or process. When the dynamics of or when the process model is truly faithfully representing the dynamics of the original process, in that case we do get time delay term eliminated from the denominator of the dead time compensator. Now, since you have got no time delay here, then you can easily design controller and the controller responses will be satisfactory as per your desire. That is the major advantage we have when we employ dead time compensators. Okay? So, let me explain a little bit also about this one, how to find the response to static load disturbances. Let me draw the block diagram. So, here we have got basically G c upon 1 plus G c G m, and we have got a load appearing here, okay, Then we have got the dynamics of the system given by g e to the power minus theta s y s. Now, I have got now g m e to the power minus theta m s, the model transfer function model of the dynamics of this process is given by g m e to the power minus theta m s. So, plus and minus, and then you have got this negative feedback. So, how to find the transfer function between y and L to see the impact or effect of, or to study the effect of static load disturbances on the output of a system. To find that, allow me please to draw its signal flow graph. So, the signal flow graph will be like this, with a gain of 1 here. I have a node over here, then I have got a gain of G c divided by 1 plus G c G m. Then I have a node here, where I am putting the nodes. Basically, the nodes are where you have got peak off or summing points or junctions. Okay. So, where you have got pick up points or summing junctions, you do get one node over there. So, let this node be this one with a gain of 1 and the signal here is L. Okay. Then the gain here is g e to the power minus theta s. I have a pick up point here. So, a node will come 1, this is the signal y s. Okay. Next, let me redraw the remaining part. So, I have got from here your yes, I will have another pickup point node here, and with a gain of, this is a gain of course minus is there. So, it will be minus g m e to the power minus theta m s. Okay. So, next it will be connected to this one with a gain of minus 1. So, thus we obtain a signal flow graph of the block diagram. Why I am going for this signal flow graph? It helps in obtaining the transfer functions using Mason's gain formula. Now, as per Mason's gain formula, we need to find the path gain P1. P1 path gain is, we have got one forward path between y and L. So, y and L, then the gain of this path is g e to the power minus theta s. What is the determinant now? Determinant is 1 minus sum of loop gains. So, how many loops I have got? 1 and 2. So, the loop gains are g c g e to the power minus theta s upon 1 plus g c g m with minus gain here. So, negative sign, then plus again we have got the second loop here. So, the loop gain of this loop with this minus minus plus. So, I will have g c g m e to the power minus theta m s divided by 1 plus g c g m. So, this is what I get. Then how much will be the cofactor delta 1? Not touching this. So, this loop gain or loop is not touching the forward path. Therefore, delta 1 can be obtained as now delta 1 is equal to 1 minus loop gain of, so not touching. So, it will be 1 plus g c g m e to the power minus theta m s divided by 1 plus g c g m. After getting all these things, now you can find the transfer function between y and L as h p 1 delta 1 upon delta. Okay. So, that will give you the transfer function between y and L, and how much that will be? That will be equal to, let me write finally, when you substitute P1, delta 1 and delta in the expression. Expression for y upon L s will be equal to g e to the power minus theta s times 1 plus g c g m minus g c g m e to the power minus theta s divided by 1 plus g c g m plus g c e to the power minus theta s minus g m g c e to the power minus theta m s. Okay. So, when you substitute and simplify, definitely you are going to get this transfer function. Now, in the event of again matching of the dynamics with that of the model, in that case g g c e to the power minus theta s minus g m g c e to the power minus theta s will be 0. This will be 0, giving us the load response function y upon L s as g e to the power minus theta s 1 plus g c g m minus g c g m e to the power minus theta s divided by 1 plus g c g m. Again we do not have time delay term in the denominator, but there is one difficulty, both the transfer functions have got the same denominator. That is one demerit associated with this. So, basically the load response is not decoupled from that of the set point response or servo tracking response. Now, Watanabe et al. Watanabe and Ito observed that when a pole is located near the origin in the left hand side of the S plane, then the response by the conventional Smith predictor controller may be sluggish enough to be unacceptable. What I mean by that? Suppose this g s e to the power minus theta s is a transfer function of the form e to the power minus phi s upon s. Then we have got a pole located at the origin, and if the pole is very near to the origin also, but of course in the left hand side of the S plane, then what happens? The time response we get from the conventional Smith predictor structure, in spite of having a good controller also, will be sluggish. What do you mean by sluggish? So, it will move very slow, you will have a sluggish response, and we do not desire such type of responses from a system. To avoid that, he proposed a modified Smith predictor controller, particularly for integrating processes. So, when this becomes an integrating process, then he employed the controller in this fashion. So, he has modified the Smith predictor, basically it is nothing but the same Smith predictor, of course having G1 H GMS upon 1 plus theta ms, where theta m is the time delay or dead time of the transfer function model. Okay. So, when this is done, then what happens? Basically, you will get improved response. Now, the ill effects of the pole at the origin can be overcome, provided we use this modified Smith predictor. Now, what type of output you will expect? Let us do little bit of analysis for this one also. So, for this structure y upon r s, or the transfer function between the output and set point input, can be found and written ultimately in the form of g g c e to the power minus theta s upon 1 plus g 1 minus g m e to the power minus theta m s g c plus GGC e to the power minus theta s. So, when G1 or G1s is equal to GMS upon S, I will skip here because it will complicate the expression. So, when G1 is equal to Gm upon 1 plus theta ms is substituted over there, then 1 y upon Rs becomes GGC e to the power minus theta s upon 1 plus GMGC upon 1 plus theta ms plus GGC e to the power minus theta s minus GMGC e to the power minus theta ms. Again, with the condition that the model matches with that of the dynamics of the actual system, that means when the model matches with the dynamics of the original system, then what will happen? Y upon Rs, this term will be 0. Okay. Then y upon Rs can be given as GGC e to the power minus theta s upon 1 plus Gm Gc upon 1 plus theta ms. So, this plays a role, major role in improving the performances, time domain performances from the system. Now, based on Watanabe's observation, many people pursued the conventional Smith predictor structure and came up with many modified Smith predictor controllers, particularly for integrating processes. One such scheme is given over here now, and this Smith predictor controller is predictor and controller is proposed by Astrom et al., where Astrom's compensator for integrating process is having another controller apart from the feed forward controller K. So, he has used basically a gain controller and a controller for improving the disturbance performances of the integrating process. Okay. So, but what has been found that the way he designs MS is not straightforward. Although better responses to step input and disturbance inputs are obtained with this scheme, the design of MS is not straightforward, and the scheme may not be applicable for other type of processes such as unstable process and so. So, the scheme may not be extendable to integrating processes. So, these are the two limitations this Astrom's Smith predictor controller have. Now, coming to another modified Smith predictor and controller. In this modified Smith predictor and controller, what do we have? You see, again for improving the disturbance rejection capability, a filter is put or a controller is put, a derivative controller or a PD controller, proportional derivative controller is injected, and this enables one to not only improve upon the set point responses, but also with the disturbance responses. Okay. So, Matausek's et al.'s compensator for integrating processes has got a PD controller in the form of Fs is equal to Kb TdS plus 1 upon 0.1 TdS plus 1, where Kb and Td are the parameters of the controller Fs. So, basically this modified Smith predictor has got two controllers, one in the feed forward path and one in the feedback path. So, with this again it is possible to control integrating process, whereas this scheme might not be able to control effectively processes having right half plane poles or unstable poles. So, this is one limitation of Matausek et al.'s compensator. Then came, based on the observation, Majhi and Atherton proposed a modified Smith predictor and controller, modified Smith predictor and controller for controlling not only integrating processes, but also unstable processes, for controlling all types of processes. So, the process could be stable, unstable or integrating, I do not mind. All type of processes with long dead time can be handled effectively with their modified Smith predictor and controller. How that looks like? So, this is what Majhi et al. Proposed. There are three controllers in the structure, and those are GC, GC1 and GC2, and they have their own functions. Now, basically GC1 is employed to stabilize open loop integrating or unstable processes. So, this controller helps in stabilization of the unstable or integrating processes. So, when g to the power minus theta s is given by a transfer function of the form e to the power minus theta s upon s or e to the power minus theta s upon 5 s minus 1, GC1 will come into picture, and when it is designed properly, then it can stabilize the unstable dynamics effectively. Now, we have got two more controllers in the loop, and those controllers have got different roles to play. GC1 is basically designed for improving the set point servo tracking or set point responses. So, servo tracking performances, and GC2 is of course designed for improving disturbance response. So, where are the disturbances we have? Basically the static load disturbance present over here. So, this is the static load disturbance, Okay. So, 3 controllers are employed to improve upon the performance of all type of processes with long dead time, and each controllers have got different roles to play. When the closed loop transfer function between the output and input y and r is obtained, I will not give the detailed description or derivations, because already I have explained how to find the transfer functions using Mason's gain formula. So, when the transfer function y upon r s is found as g g c e to the power minus theta s upon 1 plus g m g c plus g c 1 times 1 plus g c 2 g m e to the power minus theta m s upon 1 plus g c 2 e to the power minus theta s plus g c times g e to the power minus theta s minus g m e to the power minus theta m s divided by 1 plus g m g c plus g c 1. So, this is what you get the transfer function between output or Laplace ratio between the Laplace transform of output to input or reference input. When or under model matching condition, under model matching condition, when g m e to the power minus theta m s becomes g e to the power minus theta s, then that time this term will be 0, giving us y upon r h g g c e to the power minus theta s divided by 1 plus g m times g c plus g c 1. So, we get a simple transfer function with the numerator g g c e to the power minus theta s upon 1 plus g m times g c plus g c 1. Using the delay free part now, I have got 2 parts. I can write this expression as g g c upon 1 plus g m times g c plus g c 1 times e to the power minus theta s. So, we have got some delay free part and involving the time delay. So, using this delay free part, it is not difficult to design controllers G c and G c 1. How to design controllers, that we shall discuss in our next lecture, but what information we get from here is that we do get a simple expression for y upon r s. Now, similarly, the expression y upon L s can be obtained finally as g e to the power minus theta s upon 1 plus g times or g m times g c plus g c 1 into 1 plus g times g c plus g c 1 minus g m e to the power minus theta m s divided by 1 plus g g c 2 e to the power minus theta s. When you look at the denominators of both these ratios y upon r s and y upon L s, you find that you do have 1 plus g g c 2 e to the power minus theta s over here under model matching condition. Therefore, basically this modified Smith predictor has decoupled the load response from that of the set point response. We do not have same denominators, the 2 expressions have no common denominator. Therefore, the set point response has been decoupled from that of the load, static load response. That is the beauty of using this modified Smith predictor controller. On the top of that, we are able to control stable, unstable and integrating processes with date time with the help of Majhi et al.'s Smith predictor and controller. Now, Liu et al. Also proposed integrating a controller for controlling integrating processes, where they have got one pre-filter. Also they are using 3 controllers. So, motivated by Majhi et al.'s work, Liu et al. Proposed this modified Smith predictor, and the design technique for GGC G1 can be obtained from their research paper. Okay. I am not going to give you details the way they design the controller parameters, rather little bit of Liu et al. Structure I will tell that particularly the GCS is obtained as 1 plus GC1 GM times GM times 1 upon lambda s plus 1 to the power n, where the n is the order of the integrating process. And we see that the pre-filter dynamics is also not simple. So, that way if we look at the way the controllers are designed by Majhi et al. And Liu et al., definitely there are certain advantages associated with Majhi et al.'s modified Smith predictor and controller. Now, we will go to some simulation example, where an integrating process with dynamics G s is equal to e to the power minus 5 s upon s is considered. So, the process has a time delay of 5 seconds and a pole is located at the origin. Maintaining the same rise time for fair comparison of results, controller parameters given by Matausek et al., Majhi et al. And Liu et al. Are used, and the simulation results are given in this plot. The figure shows that the responses to set point and load disturbance inputs. So, we have got 3 figures. Also, it is evident from the figure that similar responses are obtainable by the 3 modified Smith predictor and controllers. So, although we have got improved disturbance performances by one controller or Smith predictor controller and so, but on an average almost similar performances can be obtained by the 3 modified controllers proposed by Matausek et al., Majhi et al. And Liu et al. Next, we shall go to the modified Smith predictors. Those are used for unstable processes with long dead time. Kwak et al. Have proposed a modified Smith predictor for controlling unstable processes with long dead time. They use 3 controllers GC, GC1 and GC2. Of course, I cannot say this is a modified Smith predictor and controller. So, they have proposed a compensation scheme where they use 3 controllers, but the controller designs are not straightforward. Now, they propose that GC can be obtained in the form of e to the power minus theta s upon tau s plus 1, where tau is a tuning parameter, and GC1 has to be g e to the power minus theta s inverse, and GC2 will be some PID controller given in the form of KC1 plus 1 upon TIS plus TDS. But it is difficult to obtain parameters for the controllers in a straightforward manner, and this scheme may not yield satisfactory performances under certain situations. Therefore, Rao et al. Proposed the modified Smith predictor including a filter in the feedback path. Although they have used the three controllers GC1, GC2 and GC3, apart from that they have a filter, a first order filter to improve robust performances of the compensator. So, robust performances can be achieved with suitable tuning parameter of tau f. This structure is not so different from that of the structure given by Majhi et al. Obviously, GC1 is there to improve the servo tracking, GC2 for stabilization and GC3 for improving the disturbance responses. But this filter is the additional stuff they have given, which is explicitly meant for improving robustness of the closed loop system. Lu et al. Proposed some compensator where they have got 4 controllers for controlling unstable processes with long dead time, and the controllers are GC1, GC2, GC3 and GC4. So, there are 4 controllers. Of course, they got motivated by Majhi et al.'s modified structure and proposed this compensator having 4 controllers, unlike that of Majhi et al., which has got 3 controllers. Now, the scheme has got, the control scheme has got one extra degree of freedom to improve particularly the disturbance response. So, the disturbance response can be improved significantly with the help of appropriate tuning of the controllers. And they have given tuning formulae which will be reproduced now for a first order plus dead time unstable process dynamics with the transfer function G s e to the power minus theta s is equal to k e to the power minus theta s upon T 1 s minus 1. So, given a first order plus dead time unstable transfer function model of this form, they have suggested the tuning parameters or tuning rules as G C 1 will have the form 1 plus T 1 divided by lambda upon k, where again lambda is set point trajectory time constant, set point trajectory time constant, and G C 2 can be computed from the expression T 1 upon k lambda plus lambda times T 1 minus root of T 1 theta T 1 lambda plus T 1 theta divided by lambda square k T 1 minus root of T1 theta, yes, plus k theta square T1 divided by theta root minus 1 times S. So, they have used a proportional controller for GC1, GC2 is a PD controller, a proportional derivative controller here PD, this is a proportional controller, and GC3 is having an expression k square upon theta root, and finally, GC4 is given by T1 upon k lambda. So, you know k, theta and T1, substitute over here and get the parameters estimated using formulae given over here. Okay? But using some rule they have found this, and we will see the type of performances we will get from Liu et al.'s compensator. Okay? Let us go to some simulation example. This simulation example basically compare the performances of Liu et al. And Majhi et al.'s modified Smith predictor controllers. So, when you consider some unstable process and design 4 controllers of Liu et al. And 3 controllers of Majhi et al.'s modified Smith predictor and controllers, and simulate the results. Some simulation results are given in this figure. You find that for fair comparison again, same speed of response is maintained. Okay? So, rise time is same, is maintained constant for both cases. Then we do observe that Majhi et al.'s Smith predictor and controller is yielding relatively poor performances, disturbance rejections, poor disturbance rejections. This poor disturbance rejection may be due to the use of a simple controller in the feedback path, the controller that is going to improve upon the disturbance rejection. I mean, Majhi et al. Is using the 3 controllers GC, GC1 and GC2, and GC2 is basically designed for improving the disturbance rejection. But since Liu et al. Are using 4 controllers, obviously there will be some improvement on the set point and disturbance responses, and as expected Liu et al.'s modified Smith predictor is giving improved performances, particularly for disturbance inputs. Let me summarize now this lecture. We have proposed or we have discussed about a number of Smith predictor and controllers for controlling stable, unstable and integrating processes, of course, with long dead time. A good number of modified Smith predictors are available in literature also, but to start with, those Smith predictor, controller and structures are enough for controlling a variety of stable, unstable and integrating processes with long dead time. The advanced Smith predictor mentioned or proposed by Majhi et al. Is found to be useful for all type of processes with long dead time. That may not be so for the modified Smith predictors proposed by others. Any point to ponder? Do we have robust stability and robust performances from the daytime compensators we have studied in this lecture? Design of controllers are done, basically the design and analysis of all the modified controllers, modified Smith predictor controllers are done with the assumption that the process model dynamics matches with the dynamics of that of the original process. That means Gm e to the power minus theta m s is equal to G e to the power minus theta s. With this assumption, we do the controller design, and in real scenario this may not be true. Unless this condition is relaxed and controllers are designed, we may not get robust stability and robust performances from the modified Smith predictor and controllers. That is all. Thanks.